Okay, I'll walk through what I learned in imperative programming in the first week, just the notes of the lectures. Okay, so this is what I summarized from the key takeaways. So we first started off with functional programming versus imperative programming, like the two different mindsets of programming, right? So what is actually the difference? FP actually has no states. So basically, it's just applying math functions to arguments. Whereas imperative programming takes successive statements that change the current state via modifying values stored in variables. So in IP, we can do I equals I plus one, whereas FP, that's definitely not allowed because it's not pure at all. So the programming language we're going to use in paired programming is scalable language, which we call as Scala. And inside Scala, there are some different programs we write. So the first one, we're just going to get started with the syntax, is going to be def factorial is equal to with our input is like n is an int, and then we return an int, and then is equal to, and the bracket, if n is equal to 0, then it's 1 else factorial n minus 1 times n, and then this is just basically the usual definition, and it's um pretty simple. I think that this one over here, I'm gonna just draw it out. This, we need to specify the return type. If there's nothing, then we return unit. And then this is like the input. We know that n is an int. And then return statement is optional because whatever is the last thing that was executed, that's just automatically taken as a return. And then inside here in Scala, there's both this equality and this EQ, which both means equal. But there's a slight difference is that the symbols mean structural equality. So it's comparing if it's the same object or value. Whereas EQ means referential equality. So is it in the stored in the same memory location? So like, for instance, if I have one and one over here, we're comparing integer, then we should use equal equal. But if it's like we're asking if it's the same thing, it's stored in the same memory, like it's that thing, then we should use EQ. And then some kind of fun matches, things we can do is like X match is equal to, and then do case, which is kind of similar to Haskell. Case zero, let maps to zero, case one leads to one. There's also syntaxes with these arrows. So for I goes from 0 to 4. So 2 basically means includes, and that if you use until, that means um, up to, but not including. So 4 is not included for until. That's the difference. And then there's always this thing that's called REPL, which basically stands for Read, Evaluate, Print, Loop Interpreter. So that's basically just something you should know. And then inside Scala, there's a pretty good thing that we use to check preconditions so that it always holds. If it doesn't hold, we do just take an error so that we don't actually run the thing. So we have require and then whatever statement we want to do. And in Scala, int is like, okay, yeah, we use int, but if we want something bigger than int, we would use big int. I think it's pretty straightforward. And then some different programs in Scala is like, for instance, we call it factorial.scala. So we end it off with Scala. And then we can write something with object. It's like object factorial. That's how we start it off. We start off with our definition of a function and our definition. And then we have our main function, which is in the form of main. And then we have our args, array, string. So that's our input. Sometimes if there's no input, we just don't care about it. And that's unit because it's just a procedure. And then we can do something like take in values. It's just like printf, input sum, scale.io, scene, read in, or we can straight take it from here. It doesn't matter. And the value of f is equal to factorial n, print line factorial f is this. In Scala, there's some things like print, print line, read int, pretty standardized. Plus is concatenation. Um, to compile in Scala, there's two options. We can use Scala C or we can use FSC. Both works depending on how you want it set up. And then this is just like an idea. This is just like the big understanding of it. But there are compile languages. C++ is an example where what it does is it converts human readable program text into an executable binary file to run. So that's like, okay, yeah, we have a program, C, and then we write it, convert it to an object file, then like to a binary file. So like that's what we do with compiled languages. Interpret languages like Python kind of does something like it takes and evaluates one line of human readable line code at a time. And then kind of Java and Scala are somewhere in the middle where we call intermediate language. So it compile into machine neutral bytecode, which are executed by the Java virtual machine using a just-in-time time compiler. So it's like an optimized version of both C++ and Python where it combines the benefits of both. And in Scala, something that's pretty unique is that it kind of just knows what data type you have. So then it can infer what it is. So we can just say val, which is basically immutable, and that our var is mutable. So we don't have to define int or double, like those kind of flow, like big int, like those kind of things. We can just say this. The only time we really have to do it is when we define the function and its return type. That's when we have to actually specify. But otherwise, for all other kind of things, we do want to just use value and variable. And then the most important part of this course is kind of invariant. It's just another way of the proper proof of correctness. So it's basically the property that is true at the start of and end of each iteration of the loop. Arrays are mutable, are objects, that's just like a FYI. Object.op, that's kind of like anything. Like most languages have this dot op. It's just like the operation, like a dot size. That's pretty standardized. Definition, yeah. I'd say this is where the invariant really comes into play, is that we first kind of identify what the invariant is, like these, and make sure that we do have a boundary for that. And then we check that if it's true at the beginning, before entering the loop, and then during the loop, while it's running, is it always true every iteration? And then when it ends, first check that it does indeed always terminate using a variant. And then when it ends, is it true? So the idea of variant is that like we want some kind of integer value that's greater than or equals 0, and it decreases each iteration as it goes down to 0. So we want something that every time decreases so that we know that it'll terminate. That's kind of our kind of way of knowing. And then there's like the more formal notation of proofs is using this person's triple. So we can write something in this form where it's like bracket P prog Q. So that basically means a program prog is executed from a state that satisfies P, then is guaranteed to terminate in a state that satisfies Q, where P is a precondition and Q is a postcondition. So this is kind of like the proof, correctness theorem proof of why it holds. And we kind of define these notation, which is kind of like V is the variant, I is the invariant, and the capitalized V is logical constraint. So we first have if pre condition init I, so the invariance true before the loop. We also have to check that the invariant holds during the loop. So that's the body. Then we have to check the result holds at the end of the loop. And then we want to check that, like basically this, and then we have the variant is greater than or equal to 0. Then this is like when the loop terminates. Then it holds that the invariant just basically holds. That's kind of just like the formal way of writing it. I don't actually like this way, but you should know it. I should definitely know it. And this is like the major difference switch between functional programming and imperative programming. Is that in functional programming, we're always doing recursion, so it's always proved by induction. Base case holds, then the inductive step, then the induction hypothesis, change it up a bit, and see if n plus 1 it can be in the same form as n. Whereas iteration is proved by correctness with invariance, is like the following above that I just talked about. So this is just another example of thing and just find the invariant at each step along the way. I think it's not worth going over. Each one is like this. Something that's pretty special about this is like here we have dot to int. That's pretty straightforward. Int is 32 bits, long is 64 bits. So that's something that I should know. Um, a really specific benefit of using Scala over, let's say, Python is that like it has both more elements of functional programming elements because we see map here, which it takes each one and maps it to it. So elements of functional programming are still implicit in Scala. And then there are also recursive definitions, which we can do like this, exponent, pretty straightforward, I'd say. And then there's also the iterative approach. I think it's the same one. You can see that the recursive definition is not very efficient. It's like, okay, yeah, I have to call the pass case, pass case, pass case. The iterative is slightly better, I'd say, but it's still pretty complex. Um, the best kind of algorithm here is actually using fast exponent, where we take advantage of the fact that like um, we can divide it by the case of 2 if it's even, and if it's odd, we just times one more to that, and it's an even as case as well. So that's like the whole thing is that we kind of just take our result, build on top of that, so it's faster. So then we go divide by 2 every time, so it's much faster. So like if we have like 2, 4, and then 4 is 16, 16 is 16 squared is 256. It grows much faster than if you were to do each step separately. So yeah, so that's what it shows here, is that exponent of 2.0 to the ninth would just basically be 2 times, because 9 is a odd number, we have to extract it out, and it would just be the exponent of 2 to the 2 times 4, because 8 divided by 2 is 4, and then we repeat this process again, and then it would be 16, and then 4 divided by 2 is 2, and then 2 times exponent of 256, we get to 1, so then we know we can end it off there, so it's 2 times 256 is equal to 512. So that's why it's so much faster than the recursion or the iterative iterative step functions. Okay, that's basically like the first chapter. I think the major takeaway from this was just introducing the invariant in the language as a general.